All right, peaceful chemistry time today. No one here to heckle the crap out of me. We're going to talk about the mole. We have a little song that we have to sing about this. I wanted to save it for when we're all here, so we will do that. But there's a song about the mole that helps us to remember the value of it. Oh, that's a good kind of double entendre. Most double entendres are sexual or at least hilarious, but this double entendre, I just mean that we know the value of it, its numerical value, and also the value of it for our hearts. You know what I mean? Like how important it is. So the song will help us remember about both of those things. Anyway, you don't know it, so the value of the mole. The mole is an amount of substance. It's one of the SI base units. It is a mole. The abbreviation is MOL, which some jokers will point out is only one letter abbreviation, but that's still technically an abbreviation. It reminds me of, you know about www. What's that stand for? This is a good quiz bowl question. World Wide Web. Let's count up the syllables. WWW. How many syllables is that? 9. It's 9 syllables. World Wide Web is 3 syllables, so that's not a very good initialism, is it? Anyway, the abbreviation for mole is MOL. The main, maybe not the main, but the first thing we do with the mole is learn how to convert it. Avogadro's number. Avogadro's number. This is named after a Italian man, I think. Amadeo Avogadro, who, I forget if I made this up or if this is like legend. It's definitely not true, but either I made it up or the legend is that the man was so ugly that there was never any official portrait of him made, but there are like borderline caricatures of him. I think the picture in your book is the only surviving indication of his appearance, and I think it is a caricature, or at least it's not a definite, like you can tell just by looking at it that that's not a real man's real face. Anyway, as I say, you'll have to look it up online later, but Avogadro's number has a numerical value. We have to know it, us here in the classroom have to know it to 3 significant figures. Let's see if I can get it slightly more precise for you. Most of the time your book just uses 3 significant figures too, but I wonder if at the very beginning it tells you with more precision. Well, I know it doesn't say the whole one because it's not, like it goes on for quite a while. I'm sure it would have decimal places even, but here we go. 6.02 21367 times 10 to the 23rd. This is the part, well obviously and this, but 6.02 times 10 to the 23rd is what I will expect you to know. Why is that important? Well, the way we use the mole is exactly how, are you familiar with this word? Maybe I spelled it badly. Dozen. You know what a dozen is. What's a dozen? 12. If I had a dozen eggs, how many eggs would I have? 12. But does it only apply to eggs? We use it for eggs quite frequently, but does it only apply to eggs? No, and that's the same thing with the mole. It's this number of anything. So in the same way that I could have a dozen softballs or a dozen tennis balls or even anything that isn't balls. It doesn't even have to just be balls. I don't know if you guys heard about dozen before. It's not all about balls. But it doesn't have to be any specific thing. I could have a dozen kids in my class. I wish I only had a dozen 8th graders in here during 5th hour. A dozen is 12. Yeah, I wish I had a dozen Mitches in my life. A dozen is 12 of anything, right? In the same way, Avogadro's number is this many, 6 times 10 to the 23rd of anything. So if I had an Avogadro's number of friends, first of all, how many human beings are there on the planet? Expressed in the same way as this.
7.
So we'll say about 7. I think it's more closer to 8 now, but 7 times,
6.
it's the 9th is a billion. So about 7 billion. So this, and remember, this is not additive. We're not adding 24 people to this, and we're not even multiplying it by 24. We're multiplying it by 10 to the 24th. So that's still, however, as many people as there are on this planet, there's more than this many people squared things in an Avogadro's number. The song we're singing will tell us
Do you
that
bet there's things on the earth that are
we did.
equivalent to Avogadro?
Oh yes. What if we did square this? What would it be if we squared it? You guys don't know how this works, right? If we square this number, what is it now? Say it. Yeah, 7 times 10 to the 18th. So do you remember how squaring works? If every human being on the planet, I guess gave birth will make it gross. If every human being on the planet proceeded forth from their uterus 7 billion, every one of the single human beings here gave birth to 7 billion more people, that would be 7 times 10 to the 18th. And that's still not even this, is it? Do you see what I'm getting at here? This is a huge, huge, huge number. What the song says is that if you had this many marshmallows, it would cover the planet, I forget however many, it's so many miles thick. Nope, not until Mitch is here. It's important for Mitch and Camden here. Camden will love it. Mitch'll secretly like it, and then he'll be like, I'm too cool for this. That's how Mitch always is. But Camden will actually like it, and she'll be nice about it. So I do want to wait for them, and it'll help you remember it, though. But this is a vast number. I'd have to look this up, but I would be surprised if this many seconds had even occurred since the dawn of the universe. Like this is an enormous number. Okay, but it's a huge number. But guess what? If you have a mole, this many atoms of pretty much anything. If you have a mole of atoms of let's say salt, that wouldn't be atoms. A mole of particles of salt, sodium chloride. Well, we just talked about how big this is, but then the song will tell you this too. A mole of salt will not even cover your hand up. A mole of atoms of salt, because an atom is such a tiny thing that it would fit right here.
I'm sorry, but who had enough time to count that many and decide that's what?
It isn't counting, and what actually you make a good point. What it is, it's based on. Yeah. Well, why do we use this specific number? Is that we had already decided that we were going to use for the atomic mass unit, or something like atomic mass unit. It may not have been called that, but we already decided that we're going to ascribe this certain mass. In fact, we had found the mass of the proton, and then we decided that we're going to have this specific amount of carbon-12. So what it's based on is 12 grams of carbon-12. You should write that down, because I know it's on the test and everyone always gets it wrong. 12 grams of carbon-12 equals 1 mole. That's what it's based on. No one could ever count this, but we decided that what we actually measure about it is mass. We certainly don't sit down and count this many atoms, but we use it as kind of like a rule of thumb in the same way that we, or makes it kind of, but if you visualize 12 dozen eggs, that's easier to visualize than 14 or 144 eggs. You know what I mean? I have a little shorthand. So what it allows us to do is describe amounts of a substance, how many atoms are in it, while really measuring mass of a substance. That's what we're going to do, in fact, right now, is the primary thing we do with it, primary here meaning first and not necessarily most important, but the primary thing we do with this is conversions. It's a conversion factor. So 1 mole equals 6.02 times 10 to the 23rd of anything, remember, but we specifically use it for, sorry, I'm going to make my 3 a little prettier. We specifically use it for particles. Why do I say particles and not atoms? Well, I'm going to tell you about the particles right now. So what the particle is, and then what the substance is, and then what we call its representative particle. So if the particle, or if the substance is an element, if it's a pure element like oxygen, no, that was not a good example. If it's a pure element like gold or tin or sodium, if we have pure sodium, what do we call one particle of that? What's the smallest particle of an element? An atom. What if it's an ionic compound, like salt? Well, we can still call it a particle, even though we usually don't. We now call it a formula unit, which we abbreviate FU. This is going to be an extremely important table for you, too, and I'll explain why in a second. What if we have a covalent compound? What's the smallest unit of a covalent compound? A molecule. Is that all of them that your book mentions? Oh, if it's ions, it's ions. Like if it's as opposed to an ionic compound, if it's just ions like dissolved in solution, we would say ions. I know I'm in your way, Peyton. I'm sorry. Well, unless I find evidence to the otherwise, I will assume that I have gotten them all.
What's after 4?
Ions, molecules, forming units, electrons. Oh, I mean, you can do it with anything. We could say how many moles of people are there in this classroom. It would be tiny. It would be times 10 to the negative 23rd. Be a tiny little number. But we could talk about moles of anything. But these are the ones we commonly use in chemistry. So 1 mole is this many of any of these things, depending on what? Well, how do I know? Let me just ask you this question to clarify. How do I know if I'm going to write this? I almost never write particles. It'll say how many particles is this many moles, but I never write particles. How do I know what I write instead?
Because you know that
Well, yeah, I know what.
particles make up.
Yeah, I know what substance it is. So, for instance, let's just do an example. If I had, this will be an easy example. How many representative particles can be found in 20.39 grams of fluorine? No, bad example. I don't want to use diatomic ones because, well, you know why. Grams of nickel. Let's not do that. I'm sorry. Let's use moles. And let's use 2.1 moles of nickel. That'll make it easier. Well, this will remind you back to the beginning of the year. I want to make sure I can do this on camera. What's my given here? This was my problem. What's my given? What should I write down first? First of all, let me ask you before we get started writing stuff. How, I'd already said, but how would be the best way mathematically to set this up to show all of our work?
With your labels.
Yeah, what's it called? I'll accept 2 answers and I'll tell you the other one if you don't. Don't call it that. Did you? Who taught you that?
Just guessing.
Oh, I hate that. No, I don't hate it. It is the same exact thing. Don't call it train tracks. What is its actual name? We did it in chemistry. We did it in physical science.
Yeah,
We did it in earth science.
It's
What's it called?
Unit
Unit conversion. Unit conversion is fine. Your book calls it, in higher level stuff, we'll always call it dimensional analysis. It's called that because we're talking about the dimensions, the units, and we're analyzing them using math. So unit conversions, though. So I'm going to set this up with the unit conversion, which I would say a young person or an idiot would call train tracks. Yeah. Okay, so you are quite young, though, Kyla. No, I'm just kidding. What should I write first, though?
2.1.
Yep, 2.1 moles, and I want you this I'm going to be really harsh on because it'll save you a lot of time later on, of nickel. So always write what substance it is too. For now, it's not going to seem super important. It's going to seem like busy work, which Mitch and Colton Mater hate, but it will come in a lot of handy later. You will be so thankful that you did this when it comes a lot of handy. It'll be handy later when it comes time for it to actually be important because you will have already been doing it. It'll come in a lot of handy, Mitch.
He won't even have his book open.
He won't even watch this video. He's not going to spend any time doing anything outside of class. He barely spends any time doing anything in class. At Mitch Canode. What's Mitch Canode's Twitter handle? Probably like Tom Brady Mitch Golf at 111. I don't care. Yeah, it's probably like Broncos Rancher Mitch 1999 at what? Is he 23 yet? Okay. Anyway, so you're gonna put your unit, which to me the unit includes the actual unit and the substance. So 2.1 moles of nickel. How do I set up a unit conversion? Well, I'm going to do this one for you in case you forgot so you don't embarrass yourself. Conversion bar, multiplication sign. I'm going to go from moles of nickel. That has to be on the bottom. It's in the numerator now. I want to get into the denominator. I'm going from moles of nickel to, well, representative particles of nickel. What's the representative particle of nickel, which is an element? Atom. To atoms of nickel. Is this going to be special for just nickel? What I'm about to write, is it going to be special just for nickel? Try again. Yeah, no, it's not going to be. It's not going to be special for nickel because remember, like a dozen, they always have not 12, but in this case, 6.27. So always, 1 mole in representative particles is always 6.02 times 10 to the 23rd. Always. If you're going from mole representative particles this is how you do it. Always given this number. 1 mole of anything is 0.02 times 10 to the 23rd. And then we're going to take our given and multiply by everything on the top, divide by everything on the bottom. Help me with my dimensional analysis. This is the part that actually matters. This is why we call it dimensional analysis. Dimensional analysis. Help do the dimensional analysis with me, Lily. What do I do? No, that's not the dimensions. Yeah, I'm going to reduce to 1 moles of nickel with moles of nickel, and I'm going to be left with atoms of nickel. So my unit to be left with is atoms of nickel. At this point, I'm going to check with my question to make sure, am I actually wanting atoms of nickel to be my answer? It says, how many representative particles can be found in 2.1 moles of nickel? So yeah, atoms of nickel is what I want.
And it is 1.26 times. Is it
10 to the 24th. Yep. Yep. E24 means times 10 to the 24th. So 1.26. Yep. This is the right sig figs. Nope, it isn't. It has to be 1.3 because our given only had 2 sig figs. But if we're using 6.02 as Avogadro's number, we can only have 3 sig figs. Just 1.3. 1.3. 1.30 would still be 3 sig figs. So 1.3 times 10 to the 24th atoms of nickel. This is good so far, right? So what can we do now? Well, we can convert from any number of representative particles to moles or moles to representative particles. Could we do this otherwise? If I had said a sample of molybdenum is found to have 3.97 times 10 to the 23rd atoms in it, how many moles is that? Could you do that one? Could you convert from atoms to moles? Yeah, it's the same thing. We would just put atoms on the bottom and therefore Avogadro's number on the bottom. Here's how it gets more powerful. We can also use mass in this, and this is where this was discovered. This is where we mostly use this, and this is where the periodic table has these goofy numbers on it from. So every element on the periodic table has a molar mass. Molar mass. This is how many grams of this element, and we will extrapolate this to substances in a second, of this element equal 1 mole. So for example, find me the molar mass of boron. If everyone would look for it, it would go faster. Find me the molar mass of boron. I thought you had good eyes. What is it? 10.012? Okay. Boron equals 10.812 grams per mole. How did Lily find that? She just guessed and happened to get this very precise number correct?
Yes.
No. How did she find it?
She looked on her view.
It's the average atomic mass of each element is also its molar mass. So we had average AMU, and now we also have molar mass measured in grams per mole, but they're found from the same place and they are numerically equivalent. Let me repeat that. You find them in the same place where?
Same place.
Yeah, but where? The periodic table, and they are also numerically equivalent. So the average atomic mass of all isotopes of boron, average, that's what average atomic mass means, is 10.812 AMU, and the molar mass of boron equals 10.812. Is that just a coincidence, Peyton, do you think? No, in fact, that's how this was discovered. When you asked who sat down and counted all these, they didn't. They used this number, which is measurable, and then divide it by this to get how many there are. I mean, that's how it's done. Not right this second. So now we have a new piece of our puzzle that we can use to solve new problems. There's still going to be dimensional analysis problems, but we have a new piece that we can use to solve them. So let's start on that kind of example. Let's say a sample of gold contains 4.91 moles. What is the mass of this sample? Step the first, not Kyla, since she did this part on the last problem. What's the first step here?
Right. 4.91 moles.
Almost.
Over.
Nope.
Times.
Nope.
Moles of gold.
Moles of gold. 4.91 moles of gold. Now, we can go on.
Times. On the bottom. Moles of gold.
On the bottom, moles of gold, and on the top? Question.
Atoms of gold.
Nope.
What is the mass? Mass of gold.
Grams of
Gold.
gold. Good, thank you.
Whoa.
Now what do I put on these lines? Should Avogadro's number ever be found?
Yes.
Lily,
No.
do we need Avogadro's number for this? What was Avogadro's number used for? Yeah, are we using particles for this? Do we have atoms or ions or formula units or anything like here? No. So what will we use as our conversion factor?
Are we going to go from...
We already are going from moles to grams. But what do we use for our conversion factor? What's our number we put on these lines?
the atomic mass?
Yeah, it's numerically equivalent to the atomic mass. We call it the molar mass. And how do I find that? Look up the periodic table. Find it.
AU?
79. 79 is not the answer. 79 is where it is what number go.
196.96.
And where do I put that?
On the
What is the unit on that? We just said over here. No, it's
grams. It's the mole.
grams per mole. And just like any fraction, if it's grams per mole, it's what does this mean? If there were numbers in this, yeah, it's 1 gram per 1 mole is what the answer is here. So this would be 197 point whatever it was it 971?
It's 196.
196 point
Yeah, 196.967.
196.96. I'm going to run out of room, so we'll just put 97. Grams in how many moles?
The
Well,
same.
no. 1 mole. 1 mole. Grams per mole. If it was 196.97 grams per mole, that's 196.97 grams per 1 mole. Okay, now, as Kyla's already up to, take our given and multiply it by everything on top and divide by everything on bottom. In the meantime, while she's doing that, dimensional analysis, not Lily. I guess Payne's doing this entire one. What should I do? How's
Eliminate moles and gold.
yeah. So moles of gold reduces to 1 with moles of gold. We're left with grams of gold. Is that what we're looking for? Yep. We go back to our problem and check. Grams of gold. Answer?
I got 967.12.
967.12. So 967 with sig figs grams of gold. Now you ask yourself, you didn't really do this on the last one because you don't have any idea what these particles are, how many there are. Was it reasonable for that much nickel? Was it reasonable for that much nickel to be more than a mole of nickel? Yeah, of course, because we had 2 moles of nickel-ish. Now, is it reasonable for 5 moles of gold to have a mass of about 1,000 grams?
Yeah.
Sure, there's nothing wrong with that. We know that 1 mole of gold has a mass of about 200 grams. So would it make sense for almost 5 moles to have 1,000 grams? Sure, of course it does. Questions about this? Could you do this? What if with mass and we had to go to moles? Could you do that?
Yes.
Okay, good. What if you started with particles and you had to go to mass? Could you do that?
No.
Yeah, you can. But could you? It's possible, but could you do it?
I don't know.
How would you do it? We're not going to do them because we could practice that on the chapter review. I don't want to waste time on the video with that. But how would we, just as a set of steps, how would we go if we started with a number of particles and we had to go to grams? What would our conversion factors be? Well, we'd start with particles. We'd eliminate particles and go to, no, because that would be particles. No.
Ions.
So we'd start with particles and go to, well, what's the similar thing that we could have, go to moles, and then go from moles to grams using this. So it is possible And we will do it on your chapter review. Okay, and then the next thing that makes this even more multi-step, Kyla, is that we can also do this, and this is easy. I mean, well, at least, did you guys all pass first grade? I think you're here as high school students, so you should have. But if you can do first grade math, you can do this. I'm going to do it in a different color. Yeah, Mitch just bullied his teacher into passing him, like he's doing here. Great job, Mitch. Okay, if we have a substance now, and I'll just make you guess, or you might have already read, but if instead of having gold or nickel or boron, if I had, for instance, methane, CH4, what could I do to find the molar mass of methane?
Oh, I know this. So you take your C, which is...
And I'm going to show you how to show your work for this. But what mathematical operation are we going to do to find the molar mass of methane?
So we're going to take here...
You're saying a lot of words. In one word, what mathematical operation? Add. Add. We're going to add. And multiply a little bit, yeah. Here's how I want you to show your work, because there was some confusion about this, about whether I can just keep it all on my calculator and take that home with me. Here's how I want you to show your work, so be very careful, because this is what I'm going to be expecting, and you will lose points if you don't do this. So what I do to find the molar mass of methane is, this will be what you write. Here I'm just showing you the thing. But C equals 12.011 grams per mole. 1.0079 grams per mole times 4. This is what I want you to show. And I'm going to have CH4 equals, well, this times 4 is about 4. Plus 12 is 16, so it's going to be roughly 16. I'll expect your math to be more precise than that, but 16-ish, 0.00, blah, blah, whatever, grams per mole. So when you show your work, list them out with their molar masses and keep them in line and add them up with its molar mass. I will be looking for units, multiplication, the actual truth of your answer, and that you have the elements written down. If you want to put a little plus sign here because you remember first grade, that's fine. I will know what mathematical operation you're doing if you don't put a plus sign.
Do we have to put the line, though?
It would be helpful for you if you did, just so you keep it separate between the elements and the substance. So this can be done, all of those two problems we just did can be done if you do it with substances as well, I mean with compounds. I expect you to show this work before you start doing your conversions. Questions about that? I'm going to briefly, that's the main math for this chapter. I'm going to briefly discuss, I expect you, we will do a lab about this, all of lesson 5, which is formulas of a hydrate. We'll do a lab about that, so that'll help you learn about that. But I do expect you to memorize the Greek prefixes for hydrates. They're the same as those for covalent compounds. But read about and memorize the prefixes for hydrates. And then also there's quite a lot of math in lesson 4 about empirical and molecular formulas. And we will do that mathematically. I don't know if I'll take a video about it, but we'll do that mathematically either before we go over your chapter review or while we're going over your chapter review. If it is the latter, that is, if we haven't gone over it by the time we're going over your chapter review, I won't expect you. Basically, if we don't have time to talk about it in class here after I finish this video, I will expect you to not necessarily have those finished, and we'll do them as part of the chapter review when we go over it, okay? Because they are a little bit math heavy and complicated. But basically what you're doing with empirical and molecular formulas is you're comparing the amounts of moles of element X in a substance to element Y in a substance and getting a ratio, which you then use to find the formula. So if the ratio of X to Y was found to be 1 to 2, then the formula is XY2. And you use the moles of the reason it's called empirical formula is because you would use experimental data to find out how many moles of each of those things was in it.
Do you mean for the formulas, the Greek prefixes, the formulas of hydrates?
Yep. Do you have questions about anything we did, though? One nice thing, Mitch, that's not the one nice thing. One nice thing that I like that apparently Mitch hates, I like that you have a little bit of the math background when I start talking about this, so you kind of know what's going on, so you don't look so like a lost animal while I'm trying to talk about this, because you've done a few of these now, or at least you've attempted to do a few of these, right? And so this, instead of being a brand new thing, really serves a more elucidatory purpose, which is that you've attempted and maybe successfully attempted, but also maybe unsuccessfully attempted some of these math problems, and this should have been elucidating, so now you know how to do it correctly. Am I off the mark? Mitch? Let's all look up into Mitch's eyes. Bye!